Hello. Thank you for joining us today. I am Megan Katz, Senior Librarian of the Science, Technology, and Patents Department at the Los Angeles Public Library Central Library. I'm so sorry for the delay. Thank you for being patient. I'd like to thank our friends group, the Best Friends of LAPL, for putting this event together. The Best Friends supports the Business and Economics Department, as well as Science, Technology, and Patents Department of Central Library. And we encourage you to join the Best Friends group and support our departments. And we are going to post a link in the chat that will give you more information about joining Best Friends and the great work that they do. Membership in Best Friends, in addition to supporting our departments, gives you access to members-only events like their upcoming open house, which is on theme with today's talk. The Best Friends will invite members and those interested in membership to join them on June 6th to try out one of Octavia Lab's new telescopes, which I will talk about in a moment, while looking down on Los Angeles from the famous observation deck at City Hall. If you're a member, you've already gotten this invitation, but if not, go to the website that was just posted in the chat to join or to sign up for the mailing list. And as for the telescopes that were just mentioned, after enjoying this Best Friends Spring event with Stephen Flanders and the Hale Telescope, you'll probably be wondering how you can get access to a telescope yourself. I'm sure you'll be thinking that. I'm happy to report that Central Library now lends telescopes to Los Angeles Public Library patrons. Telescopes are available in the Octavia Lab, which is our makerspace named for Octavia Butler, to Los Angeles Public Library cardholders for 6-week checkouts. And before I introduce our guest, I just want to mention that if you have any questions or comments or anything like that, you can just type them in the chat and then we will answer them at the end. Well, Stephen will answer them, not me, most likely. We are thrilled to welcome Stephen Flanders today for a presentation on the history of the Palomar Observatory from 1936 to the present. At the Palomar Observatory, Stephen oversees the work of 36 volunteer docents who conduct tours of the Hale Telescope, host star parties at their outreach center, and participate in a variety of special events at the observatory. So without further ado, I would love to introduce Stephen Flanders.
Thank you, Megan. Thank you very much. Hey, I work for Caltech, and I run the public outreach program at Palomar Observatory. Thank you for asking me to speak with you this afternoon. I've been talking about the observatory and about the 200-inch Hale telescope for 13 years, 10 of those as a Caltech employee. I enjoy telling the story, and now I'd like to spend a little bit of time with you talking about the science of Palomar Observatory. In the 1950s, this was a very important and very famous place, while it is now no longer so famous. After 87 years of science operations, Palomar Observatory remains an important and productive contributor to the global scientific enterprise. I'd like to organize this presentation around 3 topics. First, our mission. Second, an overview of the facilities that support our science operations, that is, the telescopes and the instruments. And thirdly, a summary of what we have contributed. We, Palomar Observatory, has contributed to science over the last 87 years. Palomar Observatory is owned and operated by the California Institute of Technology. It was built with private funds, and now its operating budget comes entirely from private sources. There are 4 points in our mission statement. We support the work of professional astronomers. We train students at the graduate level. we engineer new science instruments, and we share our results with the public. In reading this, please understand that this mission statement is aspirational in nature and does not necessarily describe what we actually do. And what we actually do can be described very simply. We convert starlight into data. We do so very reliably and very efficiently. On the Hale Telescope, we maintain a suite of science instruments, imagers, spectrographs, photometers, and others, for the use of the astronomers. During an observing run, they may use one or more of the science instruments to collect the data they need for their research. The data produced by the science instruments is our product, and the astronomers are our customers. Their home institutions pay a fee for each night of observing. The facilities, well, you see, the world-class science that we do here, it's being done at Palomar Observatory, and a complex infrastructure is needed on the mountain to support our science programs. In this section, we'll look at the location, the telescopes, and our current inventory of science instruments. Palomar's science enterprise started in 1936 when an 18-inch Schmidt wide-field telescope went into service. The dome that housed this telescope stands a quarter-mile east of the dome of the Hale Telescope. The property. Here's an overview of Caltech's property on Palomar Mountain in northern San Diego County. We are looking to the southeast across a plateau that lies at an elevation of 5,600 feet and encompasses the 2,200 acres that Caltech owns. San Diego is almost directly behind the position of the camera and 50 miles away. Los Angeles is also behind the camera, but more to the left side of the frame. LA is about 90 miles away. Let me label and describe each of the domes you see in this picture. Here we see the location of the dome we saw in that slide just a second ago. It once housed the 18-inch telescope, excuse me, that Fritz Zwicky used in the 1930s to search for supernovae. The instrument was decommissioned in 1999 and is now on display in the observatory's museum. The dome now houses weather instruments. The designation P18 represents the shorthand that we use when referring to the domes and the telescopes. Palomar Gattini IR is a near-infrared survey telescope, and it is housed in a small structure located behind P18. In this view, the building is obscured by trees. Although Gattini IR uses a 30-centimeter refracting telescope, the building in which it is mounted once housed a 20-inch telescope. Well, since we have long memories up here, the building and the telescope retain the label P20. On the left is the dome of the 48-inch Samuel Ocean wide-field Schmidt telescope. Brought into service in 1948, this telescope was used to conduct the two Palomar sky surveys, the first in the 1950s, the second in the 1980s. It now supports an optical all-sky transient survey named the Zwicky Transient Facility, or ZTF. In the last section of this presentation, we'll talk about P48's role in ZTF. To the far right is the Palomar 60-inch telescope. It was built to take some of the observing load off the Hale Telescope and was commissioned in 1970. P60, as it is known, now operates robotically as part of the ZTF system, where it uses a low-resolution spectrograph to automatically categorize discoveries made by the 48-inch telescope. P60 has a Ritchie-Chrétien optical configuration. The 200-inch Hale Telescope began science operations in 1949. It remained the largest effective telescope in the world until the first of the 10-meter Keck telescopes went into service in 1993. And the 1-meter Winter Telescope is located several hundred yards west of P200. A recent addition, its dome was not in place when this photograph was taken. Winter is a robotic, near-infrared synoptic survey telescope. Winter and Palomar Gattini IR have complementary but slightly different objectives, and we'll talk about that a little later. To summarize, there are 5 active telescopes on the mountain: 2 optical survey telescopes, 2 near-infrared survey telescopes, and 1 general-purpose research telescope. The 4 survey telescopes operate robotically and are Q-scheduled. The 48-inch Samuel Ocean Schmidt telescope is seen in the top row on the left, with the 60-inch telescope to its right. Both are now dedicated entirely to ZTF. On the second row, we see the 30-meter Gattini telescope on the left, with the 1-meter Winter telescope to its right. We refer to these 4 instruments as our discovery telescopes because their function is to repeatedly image the sky, and by comparing old photographs to the new photographs, find things that have either changed or not been seen before. The 200-inch Hale Telescope is used for spectroscopy, photometry, and imaging at visible and near-infrared wavelengths. The instruments used for imaging and photometry are mounted at prime focus at the top of the tube. Prime focus is an f3.3 modified Newtonian optical system. Spectroscopy is done at Cassegrain focus, an f16 system at the bottom of the tube. Our adaptive optics system is installed at Cassegrain focus. Observing nights are assigned to astronomers by a time allocation committee. Time on the telescope is granted to professional astronomers and graduate students who are conducting original research. In service for 73 years, this is the last major astronomical telescope to use a thick single-piece mirror cast from 14.5 tons of borosilicate glass, or Pyrex, as it was known. The mirror is not rigid. Instead, its shape is maintained by 36 mechanical levers that support the mirror from behind. It is also the largest telescope ever built on an equatorial mounting. No larger equatorially mounted telescope was ever constructed due to weight limitations. In fact, the moving parts of the telescope seen here weigh 530 tons. Yet the telescope tracks stars across the sky by rotating on high-pressure oil bearings. The oil system was a major innovation in the 1930s, and still today, it allows the telescope to turn with so little friction that the telescope's tracking is driven by a 1/12 horsepower motor. What follows then is a list of the 9 science instruments astronomers may use when observing on the Hale Telescope. These 9 instruments are grouped into 3 categories of 3 instruments each. First, 3 seeing limited instruments installed at prime focus. Second, 3 seeing limited instruments installed at Cassegrain focus. And third, 3 diffraction limited instruments installed at Cassegrain focus. Well, let's see what we can make out of this list. You see, the 3 seeing limited instruments at prime focus are primarily imaging or spectroimaging devices. We have a wide field visible light imager. We have an infrared spectrograph and polarimeter. And we have a high-speed multicolor imager photometer that's called Chimera. 3 seeing limited instruments at Cassegrain focus. CWI, the Cosmic Web Imager, is a multi-wavelength imaging spectrograph. Double spec is a single object visible light spectrograph, and the instrument has been on the telescope the longest. It has been on the telescope for more than 3 decades and is now finally being upgraded by a new device. And the third is called triple spec. It is a single object near infrared spectrograph. And the last category, the diffraction limited instruments at Cassegrain focus. We have 2 instruments here. FARO is a near infrared imaging spectrometer. PARVI is an ultrastable high-resolution infrared spectrograph and coronagraph. And those 2 instruments, in order to work, must be attached to PALM 3000, our adaptive optics system. The adaptive optics system goes onto the telescope first, and then either FARO or PARVI is attached underneath PALM 3000. Under favorable conditions, PALM 3000 allows FARO and PARVI to operate at nearly the Hale Telescope's theoretical diffraction limit, its theoretical limit of resolution. Well, moving into the third section of our presentation, the science and engineering. These telescopes and these instruments are the tools that make it possible for us to do world-class science. With that in mind, let me draw up an account of our contributions to the practice of engineering and to the science of astronomy over the last 9 decades. I'll summarize this broad topic under 6 general headings. These are the 6 areas of scientific research and engineering practice with which, over the years, Palomar astronomers have been most concerned. These are also the areas that continue to dominate our work today. I'd like to touch upon each of these areas in order, but first, well, I need to point to a limitation here. In these things, there are more actors and more subtleties than can be addressed in a short discussion like this. The goal of this presentation is to describe the roles that Palomar astronomers have played in the most important advances in astrophysics of the last 9 decades. To do this, many details must be omitted, and the work of many contributors must go unmentioned. This is especially true of the much abbreviated discussion of the work of Edwin Hubble that follows. I'll begin with the historical context. Many of Palomar Observatory's early science programs were continuations of work initially undertaken at Mount Wilson Observatory, home of the 100-inch Hooker telescope, the world's largest from 1917 until 1949. One of the most important of Palomar's early science programs built upon 2 immensely significant discoveries Edwin Hubble made at Mount Wilson in the 1920s. First, that the universe contains not one, but many millions, perhaps billions of galaxies. And second, that with only a few exceptions, every galaxy we see is moving away from us at a rate proportional to its distance. Hubble's discovery of the expansion of the universe set off a race to determine the rate at which the universe is expanding. For many reasons, Hubble was never able to arrive at a generally accepted value for what we now refer to as the Hubble constant. His estimates predicted a young and small universe that contradicted accepted theories in other fields. At one point, for example, he postulated a universe that was younger than the things it contained. His difficulties were, to a large extent, related to the limitations in design and construction of the 100-inch telescope. And the Hale Telescope was built in large part to overcome those limitations. So, with the start of science operations in November 1949, the problem of determining the rate of cosmic expansion passed to Palomar Observatory and the Hale Telescope. Observing at Mount Wilson and later at Palomar, Walter Baade took up this problem. He found 2 distinct populations of variable stars in the Andromeda Galaxy, M31. From this discovery in 1953, he produced a revised estimate of the expansion rate that doubled our understanding of the size of the universe. Even so, contradictions in the data remained, and investigations by others continued. Finally, in the late 1950s, observing with the Hale Telescope, Caltech astronomer Alan Sandage made his own calculation of the expansion rate and published a value for the Hubble constant of 75 kilometers per second per megaparsec. I know, it's startling. His estimate is consistent with recent values obtained using the Hubble Space Telescope and other ground-based instruments, which is to say, to a close approximation at Palomar Observatory, we correctly determined the age and size of the universe. This is often cited as our first and most significant contribution to the science of astronomy. Well, let me point out, just so we're all on the same page with this, point out why it is that this number, the Hubble constant, is so important. Put simply, the expansion rate is important because everything we know about the universe beyond our own galaxy depends upon knowing speed and distance. The adoption of a generally accepted value for the Hubble constant made it possible to use redshift as an indicator of absolute distance and of chronological age. As this diagram tries to suggest, the Hubble constant underlies and enables many subsequent discoveries. To illustrate this relationship, let me cite as an example a case from Palomar's science programs in which a later discovery was dependent upon Sandage's findings. The high-energy universe. Well, among the many extraordinary discoveries in the distant universe facilitated by the Hale Telescope, one of the most important was the identification of the radio-loud source 3C273 by Martin Schmidt, Alan Sandage, and collaborators in 1963. Schmidt knew this object lay at a great distance because he could see that the lines in its spectrum were strongly redshifted. In fact, using the value Sandage had obtained for the Hubble constant, Schmidt calculated that 3C273 was 2.5 billion light years away, at the time one of the most distant objects ever seen. But this distance meant that its intrinsic luminosity must be hundreds of times that of the Milky Way. No physical process known at the time could account for such a vast production of energy. In this instance, an accurate value for the Hubble constant was of critical importance for two contrasting reasons. First, Schmidt's discovery was entirely dependent upon the number Sandage had derived. Had he used Edwin Hubble's earlier estimate, for example, Schmidt would certainly have looked at 3C273's spectrum and concluded that the object was relatively close to the Earth. As such, its luminosity could have been accounted for by known physical mechanisms. But in the much larger and much older universe modeled by Sandage, it was then that the extraordinary character of 3C273 became strikingly apparent. This example shows why Sandage's publication of a correct value, what we can term a correct value for the Hubble constant, was of such great importance to the advance of cosmology and to science in general. Well, if Schmidt's discovery was dependent upon Sandage's earlier work, then it is also true that many later discoveries were dependent upon what Schmidt had done. Schmidt's discovery raised new questions that sent astronomers hurrying to find the source of 3C 273's power. Eventually, they realized that this and other similar objects lay at the centers of galaxies. Soon, this research led to black holes and to the idea that the enormous energy output of these galaxies was generated by the accretion of gas and dust around supermassive black holes that reside at their centers. We now know that supermassive black holes are located in the nuclei of virtually every large galaxy, an idea recently confirmed in images taken by the Event Horizon Telescope, which is to say, at Palomar Observatory, we opened the door. We began the process, make investigations of the high energy universe. We count this as our second major contribution to science. Excuse me. In both cases, spectroscopy was the essential tool that enabled the work of Sandage and Schmidt and many others. In fact, the analysis of the spectra of astronomical objects is the most powerful tool we have for understanding the physical processes at work throughout the universe. Spectroscopy is indispensable to the science of astrophysics. And once it was established that the universe had a beginning, spectroscopy was used to determine its chemical composition, and at Palomar to demonstrate that this composition had evolved and grown more complex over time. Well, to Caltech astronomer Jesse Greenstein, it seemed obvious that the universe had become chemically more complex. Ideas about the Big Bang gave him reason to believe that the universe had started out with a very simple set of elements. From this premise, he could prove that sometime between its simple beginnings and the present day, a great elaboration had taken place in the chemical complexity of the universe. Working on the Hale Telescope, he constructed his proof by analyzing the spectra of hundreds of stars near us in the Milky Way. The result was a catalog that enumerated and measured the chemical abundances of our galaxy and, by extension, of our universe. His work quickly led to a scientific collaboration with nuclear physicist Willie Fowler, and it was Fowler, together with Fred Hoyle and Margaret and Godfrey Burbidge, who solved the puzzle of how stars synthesize heavy elements from lighter ones in nuclear reactions in their cores. In 1983, Fowler received a Nobel Prize in Physics for his theory of nucleosynthesis. At Palomar, we consider our participation in the development of the theory of nucleosynthesis as being our third major scientific contribution. Well, and it continues. At Palomar, we continue to play a role in the exploration of the chemistry of the universe. Caltech's LIGO observatories have recently observed gravitational waves produced by neutron star mergers. The 48-inch Samuel Ocean Telescope has helped locate the afterglows produced by these events. glows that we now call kilonovae, and spectrographs on the Hale Telescope have helped analyze their chemical content. This work has in fact closed a gap in the theory of nucleosynthesis. Indeed, the theory put forward by Fowler and the others could not account for the creation of the heaviest elements. They knew that the heaviest elements must originate not in the cores of dying stars, but in unknown processes capable of generating vastly greater energies. Such processes were discussed, but Fowler knew that none of the theories being advanced were supported by evidence. But now we do have the evidence. Spectrographic analysis of recent kilonovae confirms that gold, platinum, and other heavy elements are synthesized in the merger of neutron stars. This new knowledge was enabled by the advances in technology coming from Caltech and other institutions. Indeed, technological innovation has been a hallmark of Caltech since its founding. And now Palomar Observatory's services continue to be in demand in part because Caltech is committed to the design and engineering of the world's most advanced science instruments. Often the development and prototyping of new devices is done on the Hale Telescope. As a result, Palomar astronomers always have access to the latest technology, a tradition of innovation and technical excellence runs through Palomar's history. In the 1930s, for one, Caltech developed a vacuum deposition process that puts a thin coating of reflective aluminum on the surface of the glass mirror. This replaced silvering for astronomical mirrors. Technical innovations continue. Digital astronomy was the change point, was the point at which the productivity of these instruments vastly increased over the days of photographic plates. The first electronic detector for astronomy, a pulse counting photometer, was installed on the 200-inch telescope in the 1950s. Computers for telescope control and data acquisition were introduced in the 1970s. Photo multiplier tubes were used until, toward the end of that decade, Jim Gunn and James Westphal developed the first digital camera for astronomy. Using four 800 by 800 CCD chips, four-shooter, as it was known, was able to reach magnitude 24 in 60 seconds on the Hale Telescope. Now, in the Smithsonian Institution, four-shooter was built as a prototype for the Hubble Space Telescope's wide-field planetary camera. Adaptive optics. Palomar Observatory has been at the forefront in the development of adaptive optics system. Palm 3000 has a wavefront sensor that detects errors in the light path caused by motions in the Earth's atmosphere and by defects in the optics. Operating in real time, the system calculates the precise inverse waveform and passes this information to actuators on the back of a deformable mirror. Our first adaptive optics device was commissioned on the Hale Telescope in December 1999. In fact, using the AO systems that have been developed on the Hale Telescope, we are able to image exoplanets directly. Exoplanets, planets that are orbiting stars other than our own sun. By attaching an imaging spectrograph and a coronagraph to Palm 3000, and by taking a sequence of images at increasing wavelengths, we can image an exoplanet. We can see the planet itself, and we can know what it, or at least its atmosphere, is made of. Well, I think it's a neat trick for an old telescope like this. And I should point out that the people who built it in the 1930s thought we would never be able to see planets orbiting other stars. Time domain astronomy is a branch of astrophysics that studies the lifetime evolution of a wide variety of cosmic objects. Objects of interest include novae, supernovae, gamma ray bursts, active galactic nuclei, binary stars, pulsars, and in fact, transients of all kinds. With repeated and frequent observations of an object, changes can be analyzed through time. The Zwicky Transient Facility, or ZTF, is Palomar Observatory's world-class contribution to this discipline. ZTF is described further in the section on mapping and surveys below. Well, and the last part of innovation concerns multi-messenger astronomy. There are 4 messengers that provide us with information about the cosmos: electromagnetic radiation, that is photons, gravitational waves, neutrinos, and cosmic rays. These are created by different astrophysical processes, and when astronomers synthesize the information gained through coordinated observations of an event using multiple messengers, a full and complex picture of that event can be built. The Samuel Ocean Telescope and the Hale Telescope both play important roles in this new branch of astronomy by making follow-up observations at optical wavelengths of gravitational wave events, gamma ray bursts, and other transient phenomenon in the high-energy universe, all of which is pretty far away. But we do spend time looking at things much closer to home. Palomar Observatory has a tradition of discovering and studying the small objects of our solar system. These studies have resulted in a richer understanding of our solar system's architecture. A moment ago, we saw a view of Neptune. Well, we saw a picture of Neptune taken with the adaptive optics system. Here, this system is used to observe Saturn's moon Titan as it occults a double star on December 20th, 2001. It's really a remarkable bit of footage, and it has been frozen in the PDF form that this presentation is in. Regret that we cannot see the occultations taking place. Anyway, starting in 2001, astronomer Mike Brown and his collaborators began discovering many small objects, orbiting the sun beyond Neptune, what we now call the Kuiper Belt. His discovery of Eris prompted the International Astronomical Union to alter the meaning of the term planet in a way that removed Pluto from the roster of planets. The change necessitated the creation of a new designation, dwarf planet, as Pluto, Eris, and others are now classified. Mike Brown is proud of what he's done. His Twitter handle is Pluto Killer, and he wrote a book, How I Killed Pluto and Why It Had It Coming. It's a good read on how science is done. Well, the new solar system, you see, the solar system is dynamic and changing, and we have observed our solar system as it changes and evolves ever since the observatory was opened in 1949. On March 24th, 1993, Carolyn Shoemaker discovered a comet, later named Comet Shoemaker-Levy 9, on photographic plates taken with the 18-inch telescope. Calculating its previous positions, she realized that the object had recently passed close to Jupiter. It soon became apparent that during that encounter, the comet had broken into a chain of fragments. Then, calculating its orbit forwards in time, she also realized that the comet would crash into Jupiter's atmosphere in July 1994, colliding with the planet's southern hemisphere on July 16th. The chain of fragments continued to fall into the cloud tops for 7 days. The event was viewed by professional and amateur astronomers around the world. The impact scars persisted for many months. And this event came to our attention because Carolyn Shoemaker was using the telescope to photograph the sky, to map its contents, and to look for transient objects. That brings us to our final section, mapping the Palomar sky. In fact, our survey programs have been and continue to be the most broadly impactful scientific contributions made by Palomar Observatory. The two wide-field Schmidt telescopes, the 48-inch Samuel Oschin telescope, and until 1999, the 18-inch Schmidt telescope, have been the observatory's engines of discovery. These telescopes have served this role because they have usable fields of view several hundred times that of the Hale Telescope. As seen in an earlier slide, the ZTF survey camera on the Samuel Oschin telescope records the entire visible sky once every 2 nights, while also imaging the band of the Milky Way twice a night. This old 48-inch telescope is an ideal instrument for repeatedly imaging and mapping the sky. For years, we found comets and other transient objects by conducting photographic surveys. For almost 60 years, the 18-inch Schmidt was used for supernovae searches and for mapping galaxy clusters, as well as for minor body detection. 6 major surveys were completed with this telescope before it was decommissioned in 1999. Of the 6, the Palomar Planet Crossing Asteroid Survey, which ran from 1973 to 1995, was probably the most influential and the most effective at raising awareness of the potential for asteroid collisions. During this period, Eleanor Helene and Jean and Carolyn Shoemaker discovered more than 100 near-Earth objects. In 1948, 48-inch Samuel Ocean Telescope began producing a series of astronomical surveys that remain scientifically relevant. Its first 5 decades of operation were dedicated to photographing and cataloging Palomar's visible sky, as well as to conducting supernovae searches and making stellar proper motion measurements. Currently, this telescope is dedicated to ZTF's program of repetitive imaging. By comparing recent images to older images, the system has detected thousands of transient objects, variable and pulsing stars, flares, novae and supernovae of all types, gamma ray bursts, active galactic nuclei eruptions, and a variety of other phenomena. Operating robotically, the 48-inch is the Discovery Telescope for the Zwicky Transient Facility and for the observatory. Lastly, Palomar Gattini IR has been in operation for several years. Its job is to take wide field images that are used to create catalogs of objects in the near infrared sky. No such inventory has ever existed before, and now this telescope is finding nebulae and other objects that have never been seen at visible wavelengths. Commissioning of the Winter Telescope is almost complete, and soon it will begin a synoptic survey of near-infrared transients using technologies similar to those used with the Samuel Ocean Telescope in ZTF. Well, so we've looked at the telescopes, we've described their individual roles, and we've listed the Hale Telescope's specialized science instruments. We then divided the science of Palomar Observatory into 6 subject areas and discussed at least some of the contributions and advances that have been made. I'll ask you to consider one key takeaway. Please notice the interconnectedness, the codependencies that link together all of our many disparate areas of research. In the long run, studies in one area can often inform many other studies. And, well, that's how we get science done at Palomar Observatory. With that, thank you again for giving me the opportunity to speak with you. George Ellery Hale, the founder of Caltech and the builder of the 200-inch telescope, had a motto. He said, "Make no small plans, dream no small dreams." And with that, I'd be pleased to take some questions. Any question? Well, not any questions. But thank you very much.
Thank you so much. I'm sorry I was muted. That was fascinating as expected, and we very much appreciate you joining us. While we're just watching to see if there are any questions, I do want to reiterate a thank you to our friends group, the Best Friends of LA, who support our department and the Business and Economics Department at Central Library for putting this event together. Membership in Best Friends supports our departments and gives you, all of you, access to members-only events like their upcoming open house. Best Friends invites you to join them on June 6th to try out one of Octavia Labs' new telescopes, which, as I mentioned before, are a new development in our makerspace, the Octavia Lab, named for Octavia Butler. We do have some telescopes that you can check out, and those will be, a telescope will be checked out and used at City Hall to look down on Los Angeles from their famous observation deck as part of the Best Friends Open House, which is open to members and those considering membership. If you are a member, you've already gotten this invitation, but if not, or if you're interested, go to their website, which is in the chat, to join or to sign up for the mailing list. And we will post that website again. And I just want to say thank you so much again to Stephen Flanders. That was incredibly detailed and fascinating. You did not skimp on the detail.
Can I also point out that the observatory is open again finally, and we start public weekend tours on June 10th.
Excellent. What a perfect ending. Thank you so much. And I will just look at what is happening in the Science and Technology and Patents Department, as well as Business and Economics. In our Octavia Lab, we have this Saturday, Maker Ribbons with author Danielle Davis. June is Octavia Butler's birthday celebration month. So we have a lot going on in June in the Octavia Lab. Author Ibi Zoboi wrote a book, which is a Coretta Scott King Honor Award winner, called Star Child, which is about Octavia Butler. And she will be joining us on YouTube on June 7th to discuss the book. June 10th is June Jubilee, which is library-wide at Central Library. From 10 a.m. to 4 p.m., it is a celebration of Black culture with speakers, informative workshops, live entertainment, fun interactive activities for the whole family, including discussions on health and wellness, business and financial literacy, genealogy, technology, and more. So join us for that celebration. We have a Culinary Historians of Southern California Friends group as well. And on the same day, they will present a Zoom program, June 10th, called Food Writing Unfolded. And I could just go on forever. There's so much more. But instead of going on forever, I will include a link. Here it is. If you want to find out more about these programs, you can click on the link that will be coming soon. And it looks like we actually do have a question. But before that, I just want to say really quick that our Business and Economics Department is co-hosting the Asian Pacific American Heritage Month 2023 Korean Spirits Program on May 27 with the Korean Cultural Center, featuring traditional Korean music and dance, arts and crafts, and more. And Business Department is also planning 2 programs on June 9th, a resume clinic and personal branding. Although those 2, we don't have information on our events calendar just yet, but coming soon. Otherwise, everything else I mentioned, check the events calendar link that was posted in the chat. And Stephen, I have a question for you from Courtney Lewis.
Yes.
What is the scientific discovery made by the Palomar Observatory that has excited you most over your tenure there?
Well, if I may, let me go back at least a few years before my tenure here. I think the thing that kind of most got my attention, I'll go back to the discussion of Martin Schmidt's discovery of the quasar 3C273. Well, that was a long time ago. But when I was 13 years old, just getting interested in this, I remember reading the announcement of that discovery in Sky and Telescope. I didn't understand everything that was being said, but that really stuck with me. The distance, the power, and eventually the resolution as more and more was discovered about what was going on. That was a big deal to me.
Thank you. All right. Well, once again, thank you so much to Stephen. Thank you to everyone out there in audience land for joining us. And please join us again soon for one of our many upcoming programs.
Again, thank you very much. Bye-bye.